There's 11 papers to come. That's 10 plus 1. 11 papers in the hippocampus. I couldn't possibly cover them all on individual rides or I'd be here until April. So I covered them all right now to give you a coronavirus reading list. Most of you are going to have to stay home for the next week or two. So I thought, why not? 10 papers in the hippocampus. Why not make it 11? I hope you enjoy the ride. It's coming up next. And if you do, like and subscribe. I'll see you next time on JC on a Bike. Good evening, Pittsburgh and Universe. This is JC on a Bike. My name is JC and this is Journal Club on a Bike. We're going to do a different thing today. I'm going to cover 11 papers on the way home, all having to do with the hippocampus. It's a hippocampal crash course. In fact, it's a bit of a coronavirus public service announcement for neuroscience. Assuming a lot of you are going to be staying home for the next week or two, I thought I'd give a shout out to 10 recent neuroscience papers having to do with the hippocampus, the organization of the hippocampus, the function of the hippocampus, and tie them back to some papers we found previously on JC on a Bike. First paper I want to give a shout out to is a modeling paper that implements an idea that admittedly has been in a lot of people's minds, but also in mine for a while. But I kind of lack the math skills and the computational neuroscience skills to implement any of these ideas. But the idea of having a joint attractor network between MEC and hippocampus seems like it's a good enough idea to have solved a couple of the outstanding issues between what is observed in the hippocampus and medial entorhinal cortex during navigation and experience. That's an exciting paper, and it's a neat idea. It's still a bioarchive paper though, so we'll see what it looks like when it comes out. And then I got a few papers that have to do with the dorsal ventral axis of the hippocampus. And the dorsal ventral axis of the hippocampus has in history been kind of associated with the dorsal portion of the hippocampus being more spatially oriented and the ventral hippocampus being more emotional or affect associated or something like this. And so differentiating between the function of the dorsal and ventral hippocampus, three papers this week or last have tried to look at this question. The Drew Lab in Austin, Texas has done a really neat study with newborn neurons, I believe. And they show that newborn neurons in the adult ventral and adult dorsal hippocampus are both required for conditioned fear memory. Context fear memory. Sorry, not conditioned fear memory, but context fear memory. That's a neat paper. So they're knocking down adult-born neurons' activity, not knocking them out. And so previous studies have really just ablated adult neurons. In this study, they just turn them off during training. So it's a much more nuanced manipulation of the newborn neurons in an adult. Similar result with with dorsal and ventral were being required for fear memory was also observed by another lab where they were looking at the communication between dorsal and ventral hippocampus with frontal cortex. And I believe that's the Shapiro lab in Albany, New York that's done that paper. So interestingly, dorsal ventral CA3 has also been looked at by the Sahay lab in Harvard, and they looked at CA3, so dorsal CA3 to CA1 and dorsal CA3 to the lateral septum, and then they also looked at ventral CA3 to CA1 and ventral CA3 to lateral septum. And they find that these projections play different roles in the organization of the fear memory, and what activity or what behaviors stimulating these sub-networks can reinforce. So that's a pretty cool result. Again, showing dorsal ventral organization of CA3 projections within and out of the hippocampus. That's the Sahay lab at Harvard, I believe. Windy. So earlier this week we talked about a paper who looked at, I think it was from the Chichvari lab, that looked at sharp wave ripples and the role that they play in memory. And the next few papers that I'm going to cite are looking at sharp wave ripple organization within the hippocampus. Let me get through this intersection and then I'll start it up again. So sharp wave ripples are thought to be organizing network events in the hippocampus. And we looked at that and their disruption earlier this week. And now we're just going to talk about their propagation, where they originate from. And the Lauren Frankus lab has produced another really nice result here, where they show that the sharp wave ripples, which are generated in the dorsal half and the ventral half of the hippocampus, are often, or most of the time, or even all the time, completely separate events, which would again argue or seem to lend credence to the idea that the dorsal and ventral aspects of the hippocampus function separately in some way. Yeah, here he goes. Don't keep going or anything. Push the gas pedal, whatever you do. So then, in the way that sharp wave ripples are organized in the hippocampus, we have two recent papers that show how sharp wave ripples propagate out of the hippocampus. Dietmar Schmidt's lab in Germany shows that via the subiculum and retrosplenal cortex, sharp wave ripples exit the hippocampus and propagate through the neocortex. Incidentally, Bruzaki is on that paper as second to last author, and he is on a last author paper showing the propagation of sharp wave ripples from the hippocampus to the lateral septum. So we have propagation of sharp wave ripples to the neocortex and to subcortical structures, virtually simultaneous papers. So we have sharp wave ripples and what they do in the hippocampus. We have how they interact with how they allow the interaction between the PFC and different parts of the hippocampus. And then we have an exit strategy for sharp wave ripples via two different pathways out, subcortical and cortical. So that's pretty spectacular. Now figure in this, that there's a lab that showed that very recently that the subiculum and parasubiculum are organized along a dorsal ventral axis, and they can see the sort of difference along that dorsal ventral axis in terms of the transcriptomic cell types that are there. So not only is the hippocampus differentially organized along the dorsal ventral axis, but also its output structures, subiculum and parasubiculum. Not necessarily unexpected, but definitely a nice result that goes very well with all of these recent papers, which are adding a lot to the functional connectivity understanding of the hippocampus, with looking at how shortwave ripples function and looking at what they do with in terms of synchronizing and connecting different parts of the hippocampus and different parts of the brain with the hippocampus. Super cool. I don't know what paper number we're on, but that's a lot of them, and I still got more. Even crazier, or not even crazier, but one I'm very excited about is that the Siegelbaum lab, kind of famous for having discovered CA2 or having successfully identified the functional makeup of CA2, this subregion between CA3 and CA1 in the hippocampus, they have shown that there seems to be social encoding of social identity or encoding of social information in CA2, and even more importantly to this discussion, they show that the sharp wave ripples in CA2 are encoding these memories, which is pretty cool. And they can mess with the sharp wave ripples, I believe, and mess with the social memory. So I mean, this is just a crazy list of all kinds of stuff that is definitely worth reading over your break. There's one paper that I've been excited about for a while from a friend of mine, Sandro Romani. I don't know what's going on here. And he has a bioarchive preprint out, the results of which are just driving me crazy. And so I'm just going to report it here, even though I'm quite hopeful for him that he's going to get it out soon. So what he reports is that if he looks at place cells in the hippocampus and then he depolarizes a cell, he can make that cell remap its place fields entirely. And it's not Hebbian. Wow, that guy's going like 70 miles an hour. So bidirectional plasticity that he shows in his paper seems to be dependent on the state of the synapse previously, so that synapses that were recently potentiated only have the possibility in this paradigm to be depressed, and synapses that didn't undergo a change are potentiated. It's completely non-Hebbian, and yet it completely reorganizes the firing patterns of the cells that are depolarized. Huge result, and really interesting from the perspective of thinking about what's going on during processing and how the hippocampus is so quickly and efficiently able to reorganize its network to reflect experience. And I think this, addition is really important, because up until now all the models are using Hebbian plasticity. All the models are using Hebbian plasticity rules and spike timing dependent plasticity and all this stuff that this Romani paper seems to suggest that in CA1 that there are other mechanisms of synaptic plasticity at play and available to the network. That hurts. Ow. That hurts. Ow. That hurts. Schizoid. So that is a really neat result, and I'm looking forward to it after it's reviewed. And then the final paper, I hope I didn't have that camera tilted up too high. The final paper that I want to cover is a more obscure one, but it kind of goes back to second to final paper, goes back to the findings that we saw with microglia and their role in fear memory and memory erasure. This is a group that has ablated the microglia and then let them restore themselves, and shows that during the process of this restoration, the microglia can affect short-term memory. It's a tough paper for me to recall at paper number 10, but it's worth reading, and it's like in a journal of inflammation or something, so it would have been pretty odd for some of us to have found this paper, but it's actually really cool. And so then the final paper I want to mention is a science paper. It comes from a lab whose name I don't know how to pronounce at Duke. And what they have done in the neurosurgery department of Duke is record from neocortical cells in humans and watch them recall. I'm not sure if I think they're recalling words, like a word pair. And so then they give you one of the word pair, and you need to recall the other word that was paired with it earlier. And they show that the sequences of neuronal firing that they observed when the person was memorizing the word pair is the same memory trace and order of neurons that appears when the patient is asked to recall the other word of the pair. And this is a science paper this week. It's a pretty straightforward result. It's pretty straightforward, spectacular. And it's interesting because these events that they are decoding are ripple events. So again, they fit right nicely into this 11 paper discussion. Oh, you're a terrible driver. You're a terrible driver. It's freaking raining. Would you please drive? So, 11 papers, there's your reading assignment, kids. Enjoy. I won't be able to tag all of you on this video, so it'll be up to you guys to share it with one another. Or I guess I'll just post the video 11 times on Twitter and tweet everybody out. Thanks for watching.